I'm glad we didn't record this. Yeah, you ruined my happiness of not actually having to make Matlab work. I've got nothing with F11. All right. Now look, I've got this here, but I will tell you this. All right. If you guys are on your, I'll tell you what, if you are on your Drive, if you are on Google Drive, I have in here, it's a little bit of a mess, but if you're on Google Drive, I want to do this real quick, or someone next to you has it, or not in that Google Drive, Dropbox, sorry. Okay, so remember me? Okay, if you, inside this MATLAB, if you go to the, inside our thing, the MATLAB folder, if you go to Flying Brick, let's see, okay, go back, I'm sorry. For some reason it's over in this, go to the Mars lander. I know this is a little awkward, I'm not prepared, I meant to have something here, but so be it. There's a PDF. I'm just going to open this PDF. How do I make this full screen? Go to Mars Lander. The PDF is in that Mars Lander. And if you scroll down on this, okay, this is not the important thing today, but it gives us a reference point. You scroll down and scroll down to, I guess, page 5, Flying Brick. So here I have a brick and it's flying, hence the name, Flying Brick. Not the most creative person here. This is Flying Brick, okay? You got an inertial frame out here, you got a frame attached to the brick. Well, there you go, exactly, there you go. If you can fly a brick, you're set. That's why I came up with it, okay. Flying Brick is a brick-shaped brick, and it's got one force on its F. You can see here, it's got an F out of one end of the brick, pointing in the two direction. And then if you scroll down below, I've got the equations of motion for Flying Brick. I know, a little odd. I use a ZYX phi theta psi, sort of the flip order of that aerospace standard. That's how these ones are derived. And I do it in Newton's equations. So here's the acceleration. So I get the acceleration. I solve the acceleration. Oh, yeah, here I have the accelerations in the inertial frame, and then I pre-multiply it. So in this case, I just did the acceleration in the inertial frame, and I pre-multiply it into the base frame. So here are the equations, and then here are the other equations. All right, so there are the equations. Got it? Voila. Now it's time to back to MATLAB. Back to MATLAB. So I'm ready to solve Flying Brick. I want to solve Flying Brick. I want to make it fly. So I'm going to solve Flying Brick, I'm going to use the ODE function. So the first thing I need to do is make a new script. Call it Flying Brick. And just so it, and I've got, and in Flying Brick, I've got Flying Brick code as well to refer to. So you can sit back and I'll tell you what, whatever I put here, I'll put in there as well. So in my MATLAB, I've got this Flying Brick code. So let's write some code together. So this is code. This is Flying Brick. Example of integrating or solving, integrating, solving, what are you going to say? Equation of motion for a flying brick with one force applied at one corner of a brick. Okay, I always start my programs with a clear, that clears the workspace. And then I have a this close all will close graphic windows. Just makes, when you go to plot, it makes the window plot up. And then if I do a conversion from degrees to radians, I'll stick that in. That's just stuff I usually do. Now, I'm looking at the code. I have a flying brick. But the time we have. Is what branch going to be any part of this, or is this all? At this point, it doesn't matter. What we're doing is we're picking up with a set of equations. So however you got those equations. In the example that I just showed, I happened to get those using Newton, but you could have done it. So good question. My answer was it doesn't matter, so it's not a very good answer, is it? Okay, the first thing that I have, I'm trying to decide if we want to, here's what we're going to do. I need to create a model, a solid model of my flying brick. Okay, so you can either import an STL, and I showed you that, I showed you a little bit on that, or you could draw your own. I didn't really show that, but you could draw your, create your own. Your choice. So that's going to go here. And so you'll put that here. And then when you're done, you've got some faces and vertices. And then you can always do a patch, kind of a patch command. And if you've got the model, you can just patch the thing, or if you got it in faces, vertices, you can patch, put the patch stuff in. So at the moment, I'm going to skip that step. Now, since we do have Matlab here, I suppose if we have a miracle, I'm not going to get that far. We might, well, we'll see. If we have time to come back, we will. So what I need to do next is, well, okay, let me go in some kind of order. And it's not going to be a top-down order, okay? We're going to think it through. I need to, at some point here, I need to solve the equations of motion in time. The way I'm going to do that is I'm going to integrate a set of first, well, okay. The way I'm going to do that is I'm going to use MATLAB's integration tool. Its integration tools are primarily in their ODE solver. The ODE solver, it's the ODE XX, whichever solver you want, right? MATLAB's ODE solver assumes you have a system, assumes a system of first order differential equations. So do you want to take a moment and look at a help on those? We haven't done that yet, have we? We haven't looked at those at all yet, have we? Doesn't pop up something to me, does it? Okay. I'm going to try help ODE 4.5. It'll just put a little window. We can see a few things down here. So it's got a whole bunch of ODE solvers. But what I want to do is just show you the, you can read about it here. ODE 4.5 is a fourth order Runge-Kutta method, pretty popular method. It's good for non-stiff. It says medium order method. Yeah. Okay, so it solves non-stiff differential equations. We're going to talk about it more. Here's a format for it. So you send in an ODE function, a function that the function is simply your first order differential equation. Okay, this tells you what the equation is. And we're going to do this right now. We're going to do this. The time span. That's the time over which you want to. Y, right now it's on Y. I'll use X. Y0 is the initial condition. So it's the state, your Y is your state. Y0 is the state at time 0, and then you can send it out. You can send over the and then you get back t out and y out. So y out is the solution time, and t out is the exact time at which the solution. So that's the format here. Now, here's a little down here. They've got a little example, and they do this at VDPL, this inline function. I'm going to show you. I'm going to set mine up a little differently. So, all right. So, what is it that what do our first order differential equations look like? What do they look like? You know, they look like this. Well, here, kind of, right? What do I have? We've got z, I've got x double dot, I've got y double dot, I've got z double dot. So the first thing I need to do is write these as first order differential equations. The way I'm going to do that is I'm going to make a state vector. I'll call it cap x. Let's just at the moment see with lowercase. I'm going to make a state vector cap x. It'll have terms x, y, and z. It'll have terms x dot y dot z dot. Now here I've got 3 parameters. My state vector will have 6. It will be the position of velocity of my terms. Then my time derivative will be cap x dot, and it will give me terms x dot y dot z dot, x double dot y double dot z double dot. Maybe that's worthwhile writing down. What do you think? For Matlab, I need a state vector. This thing doesn't like to. Kevin, my handwriting is getting worse here because I'm not going to flip this thing around. My keyboard locks up when I do that sometimes. So I need a state vector. So in this case, I'm going to just think about the first 3 terms at the moment: x, y, and z. That's what I've got for my generalized coordinates. Okay, and those happen to be, in this case. Oh, you know what, Doug, this is a good point too. In this case, this is x, y, z just in my inertial frame. It's the x, y, z coordinates in my inertial frame, and that's fine. It was just when I write the equations of motion, they have to be written in the body fixed frame. Hence, I projected those into the body fixed frame in the equations. Well, yeah. So I'm going to create a step. I need ODE 4-5, or any ODE needs first order differential equations. So I'm going to create a state vector x. Try to make a cap. That's going to be my state vector. Okay. And my state vector is going to consist of my generalized coordinates. And let me write it tall ways. It'll consist of x, y, z. But that's not all. It's going to be the whole state. When we say state, it has a particular meaning. The state means the position velocity. It's actually a known meaning. So I'm going to write a state vector. It's going to be x, y, z, x dot, y dot. Okay. If you will, it's q dot, if you will. Then the derivative of my state vector, x dot, is x dot, y dot, z dot, x double dot, y double dot, z double dot. All right, and I need equations for each of those. So let's write these equations, and I'll do one at a time. Okay, see that? So this is x is a vector. It's a one-dimensional array of my coordinates. Here I've got a differential. So I've got, if you will, x dot equals something. That's the equation. That's the first order difference equation. well, excuse me, x dot sub 1 equals something. That's first order differential. X dot sub 2 equals something. That's first order. All the way down to x dot sub 6 equals something. That's a first order differential equation. See that? So I just need what these equations equal. Yep. Okay. So here, what I'm doing is I'm casting this in the state space. This is the process of converting to state space. And I can always do that. I basically take a state vector, which consists of my q and my q dot. By the way, some people write it the way I write it here, q and q dot. Some people write it like q1, q1 dot, q2, q2 dot. It doesn't matter. You can choose your order. I think this makes a little more sense. Well, it really doesn't make any difference. All right, well, let's think about what the equations are. So what does x dot equal? Well, it equals cap x sub 4, right? Let me write it like this. See that? So this thing is maybe a cap x dot is just x cap 1 dot x cap 2 dot. I probably should have written it like this, 3 dot, and so on. Okay, what does cap x dot 2 or y dot equal? Well, it equals x sub 5. What does cap x 3 dot equal? X sub 6. Right, so there's 3 first order differential equations. Now, what does cap x sub 4, cap x dot 4 equal? The next one. Well, it's the x double dot. Well, what does x double dot equal? X double dot is my solution to the equations of motion. You know, it's whatever I got from the equation of motion, right? So, I can write it in terms of the cap x's. I have a bunch of terms. All right. Clay, do you have a question? Okay. Yeah. Okay. And what we are going to do is we're going to work on this today here, and we're going to pick up with this on Tuesday. But I want to get you far enough that you're up and running here. All right. So move along. So let's jump back over to Matlab. So we need that ODE solver, or we're going to put it into our ODE solver. So I'll put that term in first. So I'm going to say my cap x is going to be a state vector. So I'm going to say T cap x equal one of the ODE solvers. I'll at the moment use ODE 4.5. Oh, there. See, it says I got that. Now I'm going to put in this way at T comma x. I don't think I need that. My ODE function. So I'm going to call it my, I need an ODE function. Let's call it the EOM flying brick. Okay. And I can send it some variables if I want. Okay. So that's going to be my function call. I need my equations of motion. I need those equations that I just wrote down. I can't cut and paste. Well, yeah, cut and paste, except where do I stick them? But where do I put them in this thing, right? The ODE 4.5 is a MATLAB function. It's going to do that uncut integration. And it has to evaluate in time those equations in motion. So I'm creating, here's a little thing, hoping the Matlab help with it. If you're good at Matlab, help figure it out. I'm just showing. So we're going to make this subfunction EOM flying brick, function T and X. We can solve for equations. It'll use that to solve for those first order differential equations. Now, before I do that, there's two things I have here. I need T-span and I need X. So T-span, I'm just going to make be a vector, and I'll go from 0 steps of 0.1 to 10. So that should create an array from 0 to 10 in steps of 0.1. If you give T-span just two values, an initial and start time, it'll choose its own integration points. And if you give it an array like this, it'll evaluate at each of those. Probably I'd recommend doing the other, but it doesn't matter. We'll talk about that more if you want. And then I need X sub 0. What's X sub 0? X sub 0 is my initial condition, my state at the initial condition. So let's define my state. So X is my state vector. And my state vector X here in this case is going to equal X, Y, Z, X dot, Y dot, Z dot. And if you notice here on this flying brick example, I've actually, at the moment, dropped the three angles, okay? Yeah, it's flying piece of brick, point mask, point brick, yeah. All right, so I need X0, so I need X0, Y0, Z0, right? So, you know, it could write it out like this. X0 is, you know, where's it going to start? 0, Y0 is 0. Z0 is, let's say it starts 20 meters in the air. And then X0 dot, or let's say X dot 0, let's say it starts at rest. Y dot 0 equals 0 and Z dot 0 equals 0. But choose to do that. And then finally X0, my state is X0, Y0, and Z0. Need an equal sign, thank you. Okay, so, you know, I defined an initial condition. I defined a time. Here I made the time span be a full vector. So this ODE function will evaluate at those. And now I'm ready to call this. All right, so now what do I need to do? Well, you know, when I call that function, it'll solve. And then when it's done solving over that time, it returns me T and X are my solution.
Were you, your CapX0, is that supposed to be transposed or should it be simple?
Yeah. Well, it does, and I don't know which way it should be. So if it gives me an error, I'll go try it the other way. That is one thing. I've not figured out whether Matlab wants a row or a column vector in different scenarios. Yeah, I agree. It is a little aggravating. So yes, right now I guess I've made it a row vector. I think in this case it doesn't care, but when it gets to the ODE function, so when I get out of this, so now, you know, now once I've called that line, now I have my solution, right? Throughout time, so I can plot it, I can do whatever I want. But is that all there is? No, of course not. I haven't even put my equations in motion. Where are they? They're in this equation motion flying brick. So I need to now create a new function, and its name is going to be EOM flying brick, and its arguments are T and X. Oh, rats. And I could use different names there. I mean, I'll have to use the names I used before. And its output arguments are, come on, just let me change it. I'll call them dx dt, the x part, the derivative, the equations of motion, the derivative. Okay, and then details explanation goes there. So we need those. So the first three are easy peasy, right? I did them. The first three equations are easy. So dx dt sub 1, and I know you're saying just give me the code, I'll figure it out later. So I'm just trying to get it down. Dx dt sub 1, right? The first derivative, that one's easy. We already did it. We said over here, we said dx dt sub 1 is, the dx dt of x is x dot, and x dot was x sub 4 in our case, right? So it's x sub 4. Dx dt sub 2 is y dot, which was x sub 5. Dx dt sub 3 is x 6. All right, easy part's done. Now I need the rest. And the rest are going to be my x double dot, y double dot, z double dot. So, well, okay. Look, if flying brick is a particle, okay, I'm going to cheat here because we've got 6 minutes left, all right? We need to go through full flying brick because your Mars lander is not a point mass, okay? We're not going to slam this thing around. You're going to bring it down gently, okay? So we got to do more work. But I think in 6 minutes, if we just set it a particle, I think we can get out easy because we are in inertial frame. So we just got an mg going down. So I'm going to cheat here, okay? I'm just going to show you the equations if it's just a particle, right? This one's really easy. It's just some x, y, z, which we have, and equation of motion. And so for Newton, for the Newton part, I don't have to write those in the body fixed frame. So if I write those in the inertial frame, I just have in the x direction, if I don't have any, or we'll say the moment we'll say there's no force, it's just free fall. So in the x direction, the force is 0 and equals mx double dot. In the y direction, what is our y? Let's say we call this x, y, z. In a y direction, I get my double dot, and in the z direction, I get negative mg equals mz double dot. All right, that's the trivial case. Now, if it's the brick, it's anything but trivial, right? Because you've got to have all the angles, and those angles come from Euler's equation. So that's what we'll do. But right now, let's just see these. This was our equations of motion. Let's put these in. Got it? Okay. Okay, so x double dot, that's my dx dt sub 4. That's my x double dot. Well, what's the solution for x double dot? It's 0 divided by m, which is 0. I probably wouldn't put that in code. Dx dt sub 5. Well, I mean, why calculate it? Yeah, I can fix that though. I need it. M is something. Say it's a 10 kilogram brick. Is z 0 divided by m. Okay. I mean, if I had a force, I said there's a force on, I could add my force. And then finally, dx dt sub 6 is minus mg divided by m, or minus g. Okay. Now this, let's face it, you didn't take this class to do this. So this is trivial, but that's how I put them in. Now, if I jumped over here, you can see that the equations, you're going to have all these angles. And so we're going to have to, our state vector has to have the x's, y, z's, and these three angles. So it's going to be twice as long. But in terms of the method, so I've got these things. And then I defined m. And this function is called recursively inside the ODE function. It's called over and over and over again. Anything I put in here, I mean, there's constants, that's the way we do it. I can also pass into it. So like if I have some, and I can put stuff inside of it, do something. Let's see if this works. Oh, I need it on G. EG. And then I do think that the XDT needs, I think that it's going to want this guy in, I think this has to be a, I think it describes it, I don't know. I think it's going to, well, let's see. I'll tell you, we'll wait and see. I think it's not going to like the way, I think it's going to, I don't know if that's a row or a column. It seems like whenever I do this, it always dings me. Okay, so I think we've got stuff there. I think we're okay here. Everything should work maybe. Who knows, we'll see. We'll push the run button. T. Yeah, let's see here. I think I have to do this. I gotta do the at, yeah. Yeah. This keeps changing on me. I've got one to current. What was that, Drew? What are you saying? Yeah, don't do this. Okay. No, I gotta send T and X in.
You're missing a parenthesis at the end of the line. It's close 30, 45. Or never mind, no, it should be good.
The way I had it was they keep changing this on me. Okay, this is the way I was doing it. T comma X. This should have worked. This is what worked. Oh wait, doesn't need the comma. There we go. Okay. Oh. Hold on, I think this should work. No, I must. What's it saying? Yeah, here we go. So this worked. See, must return a column vector. So I've got to go over here and convert that to a column vector. There's two ways I can do it. Right off the bat, I can define it as a column vector, or at the end, I can convert it to a column vector. Okay, so there I've taken the transpose, got to save this, come back over. Yay. Okay, so now what it did was, well, it's, okay, I'm gonna do this again. I'm printing every time. So I've got working code. So what do I have? Well, my solution is X and T. So there's X. So I could plot, X is going to be, it's my three states. So let's just see what happens. Let's just plot terms on X. So let's just plot X sub 1, X sub row, all rows, column 1, right? That's X. And so nothing happens to X, nothing happens in the X direction, nothing happens in the Y direction. It falls in the Z. Shocked. Okay. And then we can look at the velocities. What happens to the velocity in X? Nothing. What happens to the velocity in the Y? Nothing. And what happens to the velocity in the Z? It increases linearly because it's a second order differential equation, constant acceleration. Okay, I'm clearly out of time. We need to do, this showed the most minuscule thing to get into this guy. Let me save these. You can start messing with it. This is what you do. We'll pick back up with Flying Brick on Monday where we try to work out the whole thing. But this is what you're going to be doing, okay? Guys, if you're starting to work on this ahead of time, let me know. My son did draw, if you're wanting an STL, he did draw kind of a simple little spaceship if you want it. And I think I've got that on there. It's on the Dropbox. It's on Dropbox now. Okay, everyone. Thanks for your time. I'm going to post homework solution, exam solution, and homework set, the next one. If you want to read some of those homework problems, if you have something amiss, I'm sure.
Yeah, but you need to get the scale for that wrong, you scan your face. Put your face on the chip.
Yes.
I don't think the
See,
supercomputers here
this-
are that.
This has to be. Yeah, this has to go like
Whatever.
This is right now.
Six terabytes worth of FX file.
So you got first.
Yeah, that's why I like it here. When you do like FBA or plans like that, the student code, they always limit like how many elements you run and that kind of thing.
But it's like a million.
Yeah,
They do a lot. And it runs out pretty quick. Still my way screwed up. Million elements, but it's all non-linear with compression. So like,
Yeah, did you gave it to me on paper, hard paper?
yeah. You had that.
Yeah, let me look.
More importantly, there's not a zero in the grade book.
Yeah, that's what I don't care if you get it back, but as long as you have record of it,
Well,
you turn it in.
I don't even remember what it was.
It was just the rotation and the homework.
Yeah, that one. Oh my goodness, this is embarrassing. Okay, I am not seeing it in my file, so the problem is clearly on mine. This is the bag we're living out of for this thing. Oh, it's clearly on mine. Let me check my office. Okay, let me check my office. This was chapter 3.
It was the rotation.
And that was chapter 5. Homework related. Chapter 5.
One before that, so it's just like doing schematics for everybody. So it's the one that forward.
Yeah. I copied mine and corrected
Did you
it,
get it back?
but I did not get it back.
And turn it as a hard copy?
Yeah,
It makes me wonder if I've got a whole set I haven't turned back.
yeah, I had your solutions to it, and I made a copy and corrected it because we went over in class, but I didn't get
You
mine
know, I
back.
think I do have a folder sitting on my desk that I haven't brought back. I wonder. So I need to, yeah.
Is this okay for this?
No,
I have the code back here if you want. You can send me the code. The code.
this one or one?
I'm not gonna do too much. I'm gonna look at something. So if you feel like it's working, then that's
Yeah,
fine.
it's the circular spinning box.
So I have one where I can
That's good.
fly it around, but it doesn't have any like.
Okay, so did you come up with it? Or no?
Is there no, I don't think I have it either.